If global chip production stopped today, modern civilization would begin to fail within days. Not because of smartphones or gaming consoles, but because computer chips control almost everything: power grids, hospitals, transportation, industry, communication, and finance. These tiny objects, smaller than a fingernail, are the result of the most complex manufacturing process humanity has ever created. Most people imagine a chip as a small black rectangle. In reality, a chip is an extremely precise structure containing billions of transistors packed into an area measured in nanometers. That is smaller than viruses, smaller than the wavelength of visible light. And yet every one of those transistors must work flawlessly, switching billions of times per second, for years without failure. The first crucial thing to understand is this: chips are not manufactured like ordinary components. They are not cut, drilled, or molded. They are created using a combination of physics, chemistry, optics, and quantum mechanics, inside environments cleaner than operating rooms. Each chip is the result of hundreds of repeated steps in which material is added, removed, and rearranged at the atomic level. If you like similar educational content, please like, subscribe, and share the video with your friends. Surprisingly, the entire process begins with something very ordinary: silicon, the same element found in sand. But the gap between beach sand and a silicon wafer used for chip manufacturing is enormous. Semiconductor-grade silicon must be almost perfectly pure, with impurities measured in single atoms among billions. A single uncontrolled contaminant can make a chip unusable. Even perfectly pure silicon does nothing on its own. To become a chip, it must be transformed into a semiconductor structure, where some regions conduct electricity, others block it, and others control it with extreme precision. This is not done mechanically, but by carefully manipulating how electrons behave inside the crystal lattice. Here we encounter a fundamental paradox of modern technology. The smaller the structures we want to create, the larger, more expensive, and more complex the machines must be. The most advanced chip factories cost tens of billions of dollars and rely on extreme ultraviolet light, high vacuum systems, powerful lasers, and optical components aligned with atomic precision. Chip manufacturing is not a straight-line process. Material is not slowly shaped into a final form. Instead, the silicon wafer is built up and etched down repeatedly, layer by layer. Patterns are applied, material is removed, new layers are added, and everything is aligned again and again. A misalignment of just a few nanometers can destroy an entire wafer worth millions. All of this happens in environments so clean that a single speck of dust would be enormous compared to a transistor. One particle can ruin thousands of chips at once. That is why engineers inside chip factories look more like astronauts than technicians. At this stage, electronics disappears completely, and material science takes over. Silicon may be common in nature, but the silicon used for chips is one of the most refined materials humans have ever produced. In the natural world, silicon is always bound to oxygen or other elements. To use it for electronics, it must first be separated, purified, and then reorganized into a structure that behaves in a perfectly predictable way. The process begins with the production of technical silicon, created by reducing silicon dioxide at extremely high temperatures. This material is still far too impure for electronics. Even microscopic traces of unwanted elements can dramatically change how electrons behave. For semiconductor use, silicon must reach a purity level so extreme that impurities are counted in single atoms per billion atoms of silicon. To achieve this, silicon is converted into chemical compounds, purified through repeated reactions, and then decomposed back into elemental form. This multi-step chemical process pushes purity to the physical limits of what is possible. Only then does the silicon become suitable for use in chip manufacturing. But purity alone is not enough. Silicon must also have a perfect crystal structure. In a crystal, atoms are arranged in a repeating, ordered pattern. Electrons move through this structure according to quantum mechanical rules. Any disruption, any misaligned atom, can cause unpredictable electrical behavior. That is why chip manufacturing requires single crystal silicon, not a collection of small crystals. To create this, purified silicon is melted, and a small seed crystal is slowly pulled upward while rotating. As the molten silicon cools and solidifies, atoms align themselves with the seed, forming a single continuous crystal. This process is extraordinarily sensitive. Temperature gradients, pulling speed, and rotation must be controlled with extreme precision. The result is a long, cylindrical ingot of monocrystalline silicon, sometimes over a meter in length. This ingot is then sliced into thin discs known as wafers. Each wafer is only a fraction of a millimeter thick, but can be over 300 millimeters in diameter. Cutting is followed by extensive polishing. The surface must not just be smooth, it must be flat at the atomic level. Even the slightest deviation would be replicated in every layer of the chip and lead to defects. At this point, the wafer contains no electronics at all. It is completely passive. And that is exactly the goal. The wafer must behave identically at every point on its surface so that billions of transistors can later be created with the same electrical characteristics. One crucial detail is that a single wafer does not produce a single chip. It produces hundreds or even thousands of chips at once. Every process that follows, every exposure, every etching step, every modification, happens simultaneously across the entire wafer. A single defect at this stage can destroy an enormous amount of future chips. This is also where economics enters the picture. Larger wafers mean more chips per production run, reducing cost per chip. But increasing wafer size dramatically increases technical difficulty. Maintaining crystal perfection, flatness, and mechanical stability across a large diameter is one of the hardest challenges in semiconductor manufacturing. By the end of this stage, the foundation is complete. A wafer may look like a simple, shiny disk, but it represents years of research, extreme precision, and one of the most controlled manufacturing environments on Earth. This is the point where chip manufacturing starts to feel almost unreal. We now have a perfectly flat, ultra-pure silicon wafer, but still no electronics. To turn this passive material into a working chip, engineers must create patterns measured in single nanometers, far smaller than what the human eye, or even visible light, can resolve. The tool that makes this possible is lithography. Lithography is often compared to photography, but the comparison only works at a very basic level. The wafer is first coated with a thin layer of photoresist, a light-sensitive chemical. When exposed to light, the photoresist changes its chemical behavior in a controlled way. This allows engineers to selectively remove parts of it later, revealing extremely precise patterns underneath. The pattern itself comes from a mask. A mask contains the blueprint for a single layer of the chip, never the whole chip at once. Modern chips consist of dozens or even hundreds of layers, and each one requires its own mask and its own exposure step. Every layer must be aligned with the previous ones with accuracy measured in nanometers. A misalignment smaller than a virus can render an entire wafer useless. After exposure, the wafer is developed. Parts of the photoresist are removed, leaving behind a temporary protective pattern. This pattern does not form the transistor directly. Instead, it acts as a guide, determining where material will be added, removed, or modified in the next step. Lithography is not about building electronics. It is about defining where electronics will exist. Here we reach one of the greatest paradoxes of modern engineering. Transistor features are now just a few nanometers wide, while visible light has a wavelength of hundreds of nanometers. So how can light be used to create structures far smaller than itself? The answer lies in extreme ultraviolet lithography, advanced optics, and physics pushed to its absolute limits. Instead of lenses, extreme ultraviolet systems use complex mirror assemblies operating in a vacuum. Light is reflected multiple times to focus and shrink patterns with incredible precision. The entire system must remain stable down to atomic scales. Even thermal expansion from a tiny temperature change could shift features enough to destroy the pattern. Once the photoresist pattern is formed, the wafer undergoes etching. Exposed areas of silicon or previously deposited materials are removed using chemical reactions or plasma. This step converts the temporary pattern into real, physical structures etched into the wafer. After etching, the remaining photoresist is stripped away, leaving a permanent modification. This entire cycle, coating, exposure, development, etching, cleaning, is repeated again and again. Each repetition adds or modifies one layer of the chip. Over time, a three-dimensional structure emerges, built with atomic-scale accuracy. What makes this process even more fragile is the environment in which it occurs. A single dust particle is enormous compared to a transistor. If it lands on the wafer during exposure, it can block light and ruin thousands of chips at once. That is why lithography takes place in ultra-clean rooms, with air filtered far beyond medical standards. It is important to understand that lithography does not create a chip in one moment. It creates a map, layer by layer. That map tells the next processes exactly where to place atoms, where to remove them, and where to leave them untouched. Without lithography, modern chips simply could not exist. Once the patterns are defined on the wafer, the process reaches the stage where silicon finally becomes electronics. This is where engineers decide where electricity can flow, where it must stop, and where it can be controlled. In other words, this is where transistors are created. The key step is doping. Pure silicon is a poor conductor. To control its electrical behavior, tiny amounts of other elements are introduced into its crystal lattice. Elements like boron or phosphorus are added in precisely controlled quantities, often just a few atoms among billions of silicon atoms. These dopants change how many free charge carriers exist in a region, creating N-type and P-type areas that form the foundation of every transistor. Doping is usually done through ion implantation. Ions are accelerated and fired into the wafer at carefully controlled energies. The depth, concentration, and distribution of dopants must be exact. After implantation, the wafer is heated to repair damage to the crystal lattice and to position the dopant atoms correctly. At this scale, even slight deviations can change transistor behavior. With doped regions in place, transistors are formed. Modern transistors are no longer simple, flat devices. They are three-dimensional structures with nanoscale channels, gates, and insulating layers. Electrons move through these channels according to the rules of quantum mechanics. Every transistor must switch reliably, billions of times per second, and behave identically to its neighbors. A single faulty transistor can compromise an entire chip. Once the transistors exist, a new problem appears: how to connect them all. A modern chip contains billions of transistors, and they must communicate with each other. This is solved through metal interconnects. Thin layers of metal, often copper, are deposited above the transistor layer, separated by insulating materials. These layers form a complex three-dimensional wiring network, stacking dozens of metal layers on top of each other. Each interconnect layer is created using the same repeating cycle: deposition, lithography, etching, and polishing. The result is a microscopic city of electrical highways, where signals travel at incredible speeds with minimal delay. Designing and manufacturing this network is just as challenging as creating the transistors themselves. After all layers are completed, the wafer still isn't a finished product. The next step is wafer-level testing. Automated probes contact each individual chip on the wafer to check basic functionality. Defects are unavoidable. Even in the most advanced factories, some chips fail. Those defective chips are marked and discarded. The wafer is then cut into individual chips. Each functioning chip is packaged, given external connections, and tested again. Interestingly, even working chips are not all equal. Small variations in manufacturing mean that some chips can run faster or consume less power than others. Manufacturers sort them into different performance categories before shipping. What finally reaches a smartphone, computer, or car is the end result of months of processing, thousands of precise steps, and extreme control over matter at the atomic scale. Each chip represents a combination of physics, chemistry, materials, science, and engineering pushed to their absolute limits. A computer chip is not just an electronic component. It is one of the most complex objects ever manufactured by humans, a condensed piece of modern science hidden inside nearly every device we use.